For decades, some physicists have wondered whether our entire universe began not as a simple Big Bang, but as the interior of a black hole in another cosmos. In this idea, every black hole could be a seed for a new expanding universe with its own space-time and physical laws. Tonight, we explore what it would mean if our universe lives inside a black hole, and how this radical picture tries to connect gravity quantum theory and the origin of everything we see. If you enjoy mind-bending journeys like this, please subscribe and share and tell us in the comments. Do you think our universe is just one black hole among many? Thank you for watching. Now let's begin. The idea that the observable universe might exist inside a black hole begins as a theoretical possibility in modern gravity, not as a piece of fiction. In this picture, every galaxy, star, planet and atom belongs to a region of space-time that is finite in extent and surrounded by a boundary that light cannot cross. A black hole is usually described as a compact object inside a larger universe, but here the universe itself forms the interior region, and the enclosing black hole lies in apparent reality that cannot be observed from within. The hypothesis does not rest on imagination alone. It follows from known solutions of general relativity, the theory that describes how matter and energy curve space-time. The same equations that describe a star collapsing into a black hole also describe a universe that expands from an early dense state. These are different ways for space-time to evolve under extreme conditions, yet they share key structural features. In the standard cosmological model, the history of the universe is traced back to a very early time when matter and radiation are compressed into an extremely small volume. As the equations are followed further back, density and curvature grow without bound and reach a point where classical physics no longer gives sensible answers. This boundary is called a cosmological singularity. The model does not describe what happens at the singularity itself, only how the universe behaves when it is already slightly older than that earliest instant. Black holes contain a similar element. When enough mass collapses within a small enough region, gravitational attraction becomes so strong that no signal can escape. The equations show that this process produces an event horizon, a spherical surface in space-time that divides the inside from the outside. Anything that crosses the horizon moves inward and cannot return to the external universe. Deeper inside, the same equations predict a region where density and curvature again become formally infinite. This region is the black hole singularity. Standard general relativity can follow the collapse up to this point, but cannot say what truly happens there. The presence of singularities in both cosmology and black hole physics is a sign that the theory is being pushed beyond its range of validity, but it is also a sign that these two situations share a common structure. In each case, space-time contains a region where the usual description fails and a boundary beyond which information cannot be exchanged with the rest. Cosmology introduces another important surface called the particle horizon. Because light travels at a finite speed and the universe has a finite age, there is a maximum distance from which light could have reached an observer since the beginning of expansion. This distance defines a sphere around the observer. Inside that sphere lie all the galaxies and structures from which light has had time to arrive. Beyond it there may be more matter and more structure, but signals from those regions have not yet arrived, and never will if the expansion continues in the same way. The particle horizon is therefore a practical boundary of the observable universe. No telescope can see beyond it because there has not been enough time for light from those regions to arrive. Measurements of the cosmic microwave background, galaxy surveys, and other large-scale observations all operate within this boundary and help to define its size with increasing precision. Every map that shows the large-scale structure of the cosmos is in practice a map of what lies inside this horizon. The analogy with an event horizon is straightforward. An event horizon is a boundary that nothing inside can use to send information out. A particle horizon is a boundary that nothing outside has yet had time to use to send information in. In both cases, observers are confined to a region with an effective edge set either by gravity or by the finite age and expansion of the universe. The similarity of these two horizons is more than verbal. If the total mass and energy contained within the observable universe are estimated and inserted into the standard expression for the radius of a non-rotating black hole, the result is close to the radius of the cosmic horizon, as inferred from observations. On one side, the equations describe a region whose mass determines the size of its event horizon. On the other side, the same constants of nature appear in the relation between the expansion rate, the age of the universe, and the distance to the particle horizon. When these numbers are combined, the characteristic scales nearly coincide. To many physicists, this is an interesting coincidence that reminds them how few independent scales are available in gravity and cosmology. To others, it suggests that the observable universe and a black hole with the same total mass are not just numerically similar, but may in fact be different descriptions of a single configuration of space-time seen from different perspectives. In that view, what cosmology calls the observable universe would correspond to the interior of a black hole, as seen by observers inside it, and what black hole physics calls an event horizon would correspond to the cosmic boundary beyond which no light is ever observed. The familiar Big Bang picture remains useful as a description of how the interior region evolves. The black hole picture supplies a wider context in which that evolution takes place, linking the origin of this universe to the collapse of matter in some larger inaccessible environment. The details of that external process are not known, but the structural similarity between cosmological and black hole solutions keeps the hypothesis in active discussion. The idea that everything visible resides within a single enormous black hole therefore does not stand apart from mainstream physics. It grows naturally out of the same equations that already describe the expansion of the universe and the formation of black holes, and it offers a different way to interpret the boundaries and singularities that appear in both. In the early 20th century, general relativity appears as a new way to describe gravity, replacing the idea of a force with the idea that mass and energy shape the geometry of space-time. The central equations of the theory link how space-time curves to how matter and radiation are distributed. Once these equations are written down, they allow many different solutions, each describing a possible world. Some solutions describe isolated stars and planets moving under mutual attraction. Others describe idealized universes that are the same everywhere on large scales. Among these many possibilities, two stand out for this story. One is the description of a star that collapses under its own gravity until it forms a black hole. The other is the description of a universe that expands from a hot, dense beginning. They share a mathematical core, but for a long time they are discussed as separate topics. Cosmology uses solutions in which the universe is homogeneous and isotropic. In these models, matter is spread out smoothly when viewed on scales much larger than galaxies. The geometry is encoded in a simple form, and the main quantity that changes with time is the scale of distances themselves. As time passes, this scale factor grows. Galaxies move apart not because they are flying through a pre-existing space, but because space between them stretches. Observations of distant galaxies, the redshifting of their light, and the faint glow of the cosmic microwave background support this expanding picture. When the equations that describe such a universe are followed backward in time, the scale factor shrinks and the density increases. Eventually a limit is reached where the theory breaks down and a singularity appears. The equations say that at earlier times the density and curvature become arbitrarily large, but they do not describe what happens at or before that limiting point. In parallel, other solutions of general relativity describe how a massive star can collapse. If the star exhausts its nuclear fuel, and cannot support its own weight, its outer layers fall inward. For a star above a certain mass, this collapse does not stop at a neutron star or any other known form of dense object. Instead, an event horizon forms enclosing a region from which no signal can escape. Inside that horizon, the geometry continues to evolve toward a singularity, a place where density and curvature again become arbitrarily large according to the classical equations. The description of this process from a well-behaved star to a black hole interior uses the same basic theory as cosmology. The difference lies in the symmetry and in the choice of initial conditions, not in the underlying physics. In both cases, general relativity predicts that ordinary matter, when compressed enough, leads to regions that the theory itself cannot fully describe. This shared feature makes singularities a central focus. They are not added by hand, and they are not rare exceptions. Under broad conditions, theorems show that singularities are expected in both collapsing and expanding solutions. This gives rise to an important question. If the same theory produces singularities in these two different settings, are the singularities related in a deeper way, or are they simply signs that a more complete theory is needed in every extreme situation? Some researchers explore the possibility that what looks like a singularity in classical general relativity might, in a more complete description, be replaced by a transition to a new region of space-time. In that view, the collapse of a star might not end at a true point of infinite density, but might continue into a different domain with its own internal history. Likewise, the singularity at the start of an expanding universe might be replaced by an earlier phase connected to another region in which matter is arranged differently. These ideas are speculative because no confirmed theory of quantum gravity yet exists to describe them, but they follow a clear logic. If singularities mark the breakdown of a theory rather than physical objects, then the mathematical structures on either side of them might still be meaningful. This is where the concept of a white hole becomes relevant. A white hole is defined as the time reverse of a black hole. In a black hole solution, matter and radiation can fall in but cannot escape once past the event horizon. In a white hole solution, matter and radiation can emerge from a region but nothing can fall in from outside. When the equations are examined, the description of a black hole often comes paired with a white hole part of the solution. In ordinary astrophysical situations, only the black hole side is considered physical, because it can form from realistic initial conditions. However, in speculative cosmological models, the white hole side is used as an analogue of a universe that expands out of a compressed state. The Big Bang in this interpretation resembles the interior view of a white hole region. The expanding universe is then seen as the continuation of a process that from another perspective involves matter falling through a black hole horizon. In this combined picture, the two stories told by general relativity cease to be separate. The collapse of matter into a black hole in some parent spacetime, and the expansion of a universe from a dense initial state become two parts of a single extended solution. The mathematics by itself does not prove that this is how the real universe behaves, but it shows that such a connection is allowed. The recognition that general relativity naturally supports both narratives, and that they can be joined in certain models, encourages further investigation into whether the observed universe could be the interior region of a black hole. It also motivates the search for observations that might distinguish between a universe that begins as an isolated event and a universe that continues from a collapse in a larger environment. In both approaches, the same equations quietly shape the evolution of space-time, and the differences arise from how those equations are interpreted and extended beyond the point where classical physics signals its own limits. In both cosmology and black hole physics, the word singularity appears often, yet it does not describe a concrete object that anyone can see. It is a sign that a model has been driven to its limit. In the standard description of the universe, The expansion is traced back to an early time when everything now visible is compressed into a region that is very hot and very dense. As the equations are pushed further back, density and curvature rise without bound. The model then reaches a place where it stops making sense. This place is called the initial singularity. It does not have a location in ordinary space because space itself shrinks away as the calculation proceeds. Time, as measured by clocks that move with the general flow of matter, cannot be extended to earlier values within this framework. In simple terms, the model draws a boundary and states that it cannot describe what lies beyond. In the case of a black hole, the situation is different in detail but similar in spirit. Here the story begins with a massive object that collapses. When the mass passes within a certain radius, an event horizon forms. An observer who remains outside can still describe the collapsing surface as it slows and fades, but an observer who falls inward experiences a finite time before reaching a region where tidal forces and curvature grow very large. In the mathematical solution, this process ends at a singularity inside the horizon. Once again, density and curvature become unbounded, and the equations cannot be followed any further. This singularity sits at the center of the black hole, in the simplest non-rotating case, and every path followed by matter or light inside the horizon heads toward it. In both stories, general relativity predicts its own breakdown. The singularity is not a point that can be probed directly. It is a boundary of predictability where the theory cannot say what happens next. The presence of such boundaries at both the beginning of the standard cosmological model and the interior of black holes is a strong hint that they share a deep connection. It suggests that the extreme conditions at the origin of the universe and the extreme conditions in a collapsed object are not just similar numerically, but may belong to the same family of solutions. To make sense of this idea, it is useful to separate what is firmly established from what is speculative. It is firmly established that general relativity combined with reasonable assumptions about the nature of matter leads to singularities in both expanding and collapsing situations. This result is expressed in singularity theorems which show that once certain conditions are met, the formation of such boundaries is unavoidable within the theory. It is also firmly established that classical general relativity does not include the quantum effects that become important at very high densities and very small scales. Therefore, no one expects the singularities of the classical model to be literal points of infinite density in the real universe. They are markers that a more complete description is needed. The speculative step concerns what replaces these markers when a full theory of quantum gravity is considered. One proposal is that the singularity at the start of an expanding universe corresponds to a bounce or transition from an earlier phase. In this view, matter and space-time approach extreme conditions, but instead of collapsing into an undefined state, they undergo a change that creates a new expanding region. Another proposal is that the singularity inside a black hole also corresponds to a transition, not an endpoint. Matter that falls into the black hole does not remain frozen at a point. It continues into a new domain that from the inside looks like an expanding universe with its own history. Both ideas use the same basic pattern, replacing a breakdown in the classical theory with a bridge to another region. When these two pictures are combined, a coherent scenario emerges. The singularity in a parent universe created by the collapse of a massive object into a black hole becomes the starting point for an interior universe that expands from a hot, dense state. From the outside, in the parent universe, the process looks like ordinary gravitational collapse. From the inside, in the new universe, the process looks like a big bang. The singularity that appears in the classical description of the black hole interior is then understood as an artifact of ignoring quantum effects, while the physical process involves a very rapid transformation of matter and geometry. The initial singularity of the interior universe is likewise replaced by the earliest moments of this transformation. In this way, what appear as two separate singularities in two separate models are reinterpreted as different aspects of one event. The singularity at the center of a black hole and the singularity at the beginning of a universe are no longer independent. They are two sides of a single connection between a collapsing region and an expanding region. This does not solve the problem of singularities in a final sense, because the exact form of the bridge is not yet known. It does, however, offer a framework in which the repetition of singularities across different solutions is not an accident. It becomes a sign that the theory is pointing toward a more unified picture. In such a picture, the universe that is observed today may be one of many interior regions, each born from the collapse of matter in a larger environment. Every singularity that appears in the classical model then hints at a possible link between different domains of space-time, and the singularity at the beginning of this universe hints that it too may have emerged from the interior of a black hole in a parent cosmos. For the black hole universe hypothesis, this way of thinking is central. It treats the singularity not as a wall that ends the story, but as a junction where one part of space-time gives rise to another. The interior universe inherits conditions set by the collapse in the parent region, such as its total mass and perhaps its rotation. In discussions of both the universe and black holes, horizons appear as precise mathematical features rather than visual borders. An event horizon around a black hole is defined as the boundary from which no light or signal can ever reach faraway observers. Once matter or radiation crosses this surface, every possible path in space-time curves inward. The escape routes that exist outside the horizon simply do not exist inside it. Nothing in the classical description can carry information back out across that boundary. The event horizon therefore separates two regions with very different causal behavior. Outside events can in principle influence distant parts of the universe given enough time. Inside events are confined to a future that ends at the singularity. This separation is not a physical membrane, and it is not made of any particular material. It arises from the way space-time itself is shaped by mass and energy. General relativity describes this structure through the geometry of paths that light and matter can follow. At the horizon, those paths tilt so far inward that all future motion points toward the central region. For an external observer, signals sent from near the horizon arrive with increasing delay and loss of energy. For an infalling observer, however, the passage through the horizon occurs in a finite time, with no local sign that anything special has been crossed. The difference lies in the global arrangement of space-time, not in any sudden change in local physics. Cosmology introduces another type of horizon called the particle horizon that also reflects the limits of influence in space-time. Because light travels at a finite speed and the universe has existed for only a finite time, there is an outermost distance from which light can have reached a given observer. That distance multiplied by the expansion history of the universe defines a boundary in space. Inside this boundary are all the galaxies and structures that have had time to send light that arrives by the present day. Outside it lie regions that may or may not contain similar structures, but whose light has not yet arrived and never will if the expansion continues in the same way. The particle horizon is therefore the edge of the observable universe for that observer. No improvements in telescope technology can reveal what lies beyond, because the limitation arises from the finite age of the cosmos, not from any imperfection in instruments. The existence of a particle horizon means that even in a universe that extends indefinitely, each observer occupies a finite region of visibility. Every map of the large-scale structure is a map of that region. Beyond its edge, the theory can extrapolate but cannot confirm. The analogy between the particle horizon and the event horizon becomes clearer when they are compared in terms of information flow. In a black hole, information about events inside the horizon cannot reach the outside universe in the classical theory. In cosmology, information about events beyond the particle horizon cannot reach the observer inside. In both cases, there is a region about which no direct signal can ever be received. The difference is that in a black hole, the hidden region lies inside a sphere, while in cosmology, the hidden region lies outside a sphere. Mathematically, both situations involve surfaces that divide space-time into parts with different causal relationships. The similarity becomes more than qualitative when the scales involved are estimated. The radius of a non-rotating black hole is proportional to its total mass and energy. If the total mass and energy contained within the observable universe are summed and used in this relation, the resulting radius is close to the distance of the cosmic horizon inferred from observations. On one side, the relevant quantity is the size of an event horizon surrounding a collapsed object. On the other side, the relevant quantity is the maximum distance that light has travelled in an expanding universe. Yet the characteristic lengths that emerge from these two contexts are of the same order. This numerical match does not by itself prove that the universe sits inside a black hole, but it shows that the observable universe behaves in terms of scale, an enclosed mass, as if it could be the interior of such an object. The event horizon of the hypothetical parent black hole would then coincide from the point of view of internal observers with the particle horizon of their universe. Every line of sight would end at the same distance, because that is where light paths meet the internal projection of the horizon. In that picture, the fact that nothing can be seen beyond the cosmic boundary is not only a matter of finite age and expansion, but also a direct consequence of living inside an enclosed region of space-time. Another horizon sometimes discussed in cosmology is the cosmic event horizon that appears in models where the expansion accelerates due to a non-zero cosmological constant or similar effect. In such models, there are regions that are currently visible, but will eventually pass beyond the range from which signals can ever be received in the future. This horizon represents a different kind of limit related not to the past reach of light, but to the future reach of communication. It shares with the black hole event horizon the feature that some events are permanently excluded from causal contact. Together, these various horizons show that the universe is not a place where information can flow freely without restriction. The structure of space-time sets firm boundaries on what any observer can in principle know. Whether those boundaries are interpreted as the edges of an isolated universe, or as the inner surface of a larger black hole, they play the same role. They define the region in which measurements and observations can be carried out, and they leave whatever lies beyond as a subject for theory, constrained only indirectly by the behaviour of the visible domain. As understanding of these horizons improves through observation and theory, the picture that emerges is one of a cosmos whose limits are precise, measurable and deeply tied to the same gravitational laws that create black holes. When cosmologists describe the large-scale universe, they measure not only how fast it expands, but also how much matter and energy it contains. Galaxies, gas, dark matter, and the smooth background of radiation all contribute to an overall density. From observations of galaxy cluster in the cosmic microwave background and the brightness of distant supernova, an average density can be inferred for the part of the universe that can be seen. Multiplying this density by the volume inside the observable horizon gives an estimate of the total mass and energy enclosed. The result is a very large number expressed most easily as a power of 10, but it is finite and well constrained. With this estimate in hand, one can perform a simple thought experiment using the known behaviour of black holes in general relativity. For a non-rotating black hole, the size of the event horizon depends directly on the total mass contained within it. Given the mass, there is a specific radius at which the escape speed from the surface would equal the speed of light. If more mass were packed inside a smaller radius, gravity would be so strong that not even light could escape, and an event horizon would form. This radius is often called the gravitational radius. It appears in many calculations involving compact objects and plays a central role in the description of black holes. The thought experiment asks a straightforward question. If all the mass and energy inside the observable universe was somehow compressed into a single object, what would the gravitational radius of that object be? When the estimated mass of the observable universe is inserted into the relation between mass and gravitational radius, the answer that emerges is striking. The radius of the corresponding black hole is of the same order as the radius of the observable universe itself, as inferred from the distance to the particle horizon. In other words, the size of the region that can be seen defined by how far light has travelled since the beginning of cosmic expansion is similar to the size of the event horizon that a black hole with the same mass would have in general relativity. Two very different constructions produce nearly the same characteristic scale. One construction uses the dynamics of an expanding universe built from a smooth distribution of matter and radiation and shaped by the cosmological constant and other energy components. The other construction imagines a static black hole with a given mass and asks at what radius an event horizon would form. The close agreement between these two scales is often described as a coincidence. It can be explained in part by the fact that the present universe has a density not far from a critical value, at which its expansion sits between rapid recollapse and rapid dispersal. In a universe with this kind of density, the age, the expansion rate, and the enclosed mass take on related values, and it is less surprising that some characteristic scales align. Still, the numerical similarity invites a more speculative interpretation. If the observable universe behaves in terms of its mass and size as though it were the interior of a black hole, perhaps this is not just a coincidence of units. In the black hole universe hypothesis, the match between the cosmic horizon and the gravitational radius is taken as one of several hints that the universe may actually be the inside of a black hole formed in a larger environment. In that scenario, the event horizon of the parent black hole and the particle horizon of the interior universe are essentially the same surface described from two viewpoints. External observers in the parent universe would see an object with a certain mass and an event horizon of a certain radius. Internal observers living in the expanding region beyond the classical singularity would see a universe with a finite visible extent, bounded by a particle horizon at nearly the same radius. The equations that relate mass radius and gravity do not care which description is used. They simply connect the physical quantities. It is important to note that not all researchers accept this interpretation. Many consider the mass-radius match to be an interesting but expected outcome of combining general relativity with the observed density of the universe. In this view, the similarity does not point to a hidden identity between the universe and a black hole. It is simply a reflection of how a universe close to the critical density behaves. Others argue that the black hole universe picture offers a useful way to reframe familiar quantities and that it might eventually guide the search for a deeper theory that unifies cosmology and black hole physics. For now, the mass-radius coincidence sits between these perspectives. On one hand, it is fully compatible with the standard cosmological model and does not require any change to how that model is used to interpret data. On the other hand, it keeps open the possibility that the visible universe could be understood as the interior of a black hole, whose total mass and size are already encoded in the measurements that define cosmic history. The same numbers that describe the expansion and composition of the universe may also describe the properties of a parent object that cannot be seen directly, but whose horizon coincides in scale with the boundary of what can be observed. Another layer of nuance comes from the fact that the standard cosmological models and the simple black hole solution differ in their symmetries and matter content. The familiar black hole description assumes a vacuum outside the collapsing mass and a static geometry once the black hole is formed. The expanding universe, by contrast, is filled everywhere with matter and radiation, and changes with time as distances grow. To connect these two descriptions, more elaborate models are needed in which an interior expanding region is joined across an appropriate boundary to an exterior region that looks like a black hole in a larger spacetime. In such constructions, the relation between the enclosed mass and the size of the boundary still plays a central role. The fact that simple estimates already bring the scales into close alignment suggests that more refined models will have to account for this match, whether they interpret it as a coincidence or as a sign of a deeper identification between the cosmic horizon and an event horizon in a parent universe. As the parallels between black holes and the expanding universe become more apparent in the equations of general relativity, some theorists begin to ask whether these similarities could form the basis of a new way to think about cosmology. In the decades after general relativity is introduced, attention first turns to understanding individual stars, gravitational collapse, and the nature of singularities. At the same time, cosmology develops rapidly as observations confirm that galaxies are receding from one another, and that the universe is expanding on large scales. For a while, these lines of research proceed along largely separate tracks. Black holes are treated as exotic endpoints of stellar evolution, or as central engines in quasars, while cosmology focuses on the history of the whole universe, from an early hot state to its present structure. Gradually, however, the recognition that both black holes and the universe share features such as singularities and horizons encourages a more unified perspective. The idea that the Big Bang might be related to a black hole interior begins to appear in scientific discussions. Early proposals suggest that what appears to be a singularity in one description could in a more complete picture represent a bridge between different regions of spacetime. In this context, the term black hole cosmology emerges as a way to name models in which the universe is understood as the interior of a black hole formed in a larger parent spacetime. In these models, the familiar description of an expanding universe is not discarded. It is reinterpreted as the internal view of a process that from outside would look like gravitational collapse. Matter in the parent universe falls inward, crosses an event horizon, and heads toward conditions where classical general relativity predicts a singularity. Instead of ending there, the process continues through a regime where quantum effects become important. The result in the interior region is an expanding universe that begins in a hot and dense state. Observers within that region can trace their history back to an early time that appears as a beginning, but in the extended picture it is a continuation of events that took place in the parent spacetime. A central element of black hole cosmology is the reinterpretation of the Big Bang. Rather than treating it as the absolute start of existence, these models treat it as a transition. On one side of the transition lies a collapsing region of a parent universe. On the other side lies an expanding interior universe. From within the interior, the transition appears as an initial moment beyond which the classical equations cannot be extended. From the larger viewpoint, it appears as the formation and interior development of a black hole. The white hole concept provides a useful language for this idea. A white hole is a mathematical solution in which matter and radiation emerge from a region that cannot be entered from outside. If the interior of a rotating black hole connects after there would be singularity to such a region, then the expanding universe can be described as the interior of a white hole that is itself linked to a black hole in the parent spacetime. Black hole cosmology does not claim that every detail of this picture is already known. It acknowledges that the physics of extreme densities where quantum gravity becomes important is not yet settled. Instead, it uses the known structures of general relativity as a guide. The presence of singularities horizons and conserved quantities such as mass and angular momentum suggests that certain features of the parent black hole could be inherited by the interior universe. The total mass of the collapsing object would determine, in this view, the overall mass and energy content of the interior universe. The rotation of the parent black hole would set a preferred axis that might leave subtle traces in the distribution and motion of matter on the larger scales. Even without a full theory of the transition, these qualitative links give black hole cosmology a framework in which to generate testable ideas. Historically, the reception of these models within the broader scientific community is cautious. Standard cosmology already explains many observations with a relatively simple set of assumptions, and alternative models are expected to match or improve upon this success before they are widely adopted. Black hole cosmology therefore develops at the margins explored by researchers interested in connections between gravitational collapse quantum gravity and the origin of the universe. It remains a minority viewpoint, yet it benefits from the fact that it is grounded in established equations and that it offers potential explanations for certain numerical coincidences and structural features of the universe. Among these are the similarity between the radius of the observable universe and the gravitational radius of a black hole with the same mass and the presence of horizons and apparent singularities in both contexts. The field also intersects with ideas about baby universes in which each black hole might give rise to a new expanding region with its own physical parameters. In such scenarios, a larger cosmological structure could contain many interior universes, each isolated by its own horizon. The observable universe would then be one member of a much wider family. While this picture remains speculative, it frames familiar questions in a new way. Instead of asking only how the universe evolves from its earliest known state, black hole cosmology asks how that state itself might be the outcome of processes in a broader space-time. It invites consideration of the possibility that the universe is not an isolated system, but part of a chain of structures linked by black holes and their interiors, with each link governed by the same fundamental laws of gravity and matter. From the observational side, interest in these models is renewed whenever new data reveal small tensions with the simplest cosmological assumptions. Measurements of the expansion rate, the distribution of galaxies, or the detailed pattern of temperature variations in the cosmic microwave background sometimes show discrepancies that are not yet fully understood. Black hole cosmology offers one possible context in which to interpret such features. It suggests that some properties of the observable universe, including its total content and any large-scale alignments, might be inherited rather than arbitrarily set long ago by the mass spin and environment of a parent black hole in a larger unseen cosmos. White holes arise first as a mathematical curiosity in the same theory that predicts black holes. In general relativity, if a set of equations admits a solution, then the time reverse of that solution is usually also allowed. A black hole in the simplest description is a region of space-time from which matter and radiation can enter, but cannot escape once they pass the event horizon. The time-reversed version of this behavior is a region from which matter and radiation can emerge, but into which nothing from the outside can fall. This is the definition of a white hole. In the equations, the white hole region is linked to the black hole region, forming different parts of a single extended space-time structure. For many years, white holes are not considered realistic astrophysical objects. There is no known process in the ordinary universe that would be expected to produce them, and any matter emerging from a white hole would quickly interact with its surroundings. The concept remains mainly as a formal partner to the black hole solution. However, when cosmologists think about the early universe as an expanding region that appears to emerge from an extremely compact state, the white hole description becomes more relevant. The behavior of matter and radiation streaming out from a white hole region resembles in broad terms the behavior of matter and radiation in a universe that expands from a dense, hot beginning. Both situations involve a one-way flow of information. In a black hole, information about events beyond the horizon cannot reach the outside. In a white hole, information about the external universe cannot reach the interior source region, but signals from that source can spread outward. In an expanding universe, information about events before the earliest describable moment cannot be recovered, but information from that moment onward fills space as time passes. The Big Bang model describes the universe as it evolves from a very early state where density and temperature are high. It does not describe what, if anything, comes before that state. From the point of view of observers who live in such a universe, all directions in space look similar on large scales, and the expansion appears to proceed everywhere at once. If this expanding region is identified with the interior of a white hole, then the earliest moments of cosmic history correspond to the arrival into this interior of matter and radiation that have passed through an extreme gravitational region connected to a black hole in a larger space-time. The white hole serves as the outgoing side of a process that in the parent environment looks like the final stages of collapse. In this picture, a black hole in the parent universe and a white hole region in the interior universe are two aspects of one continuous solution. Matter falls inward through the black hole horizon, encounters conditions where classical general relativity predicts a singularity, and then when quantum effects are taken into account, transitions into a new domain. From the perspective of that domain, matter and radiation appear to emerge from an initial region and spread outward as space itself grows. The mathematical structure of certain idealized black hole solutions supports this idea. When a non-rotating black hole is written in a coordinate system that covers more than just the external region, it includes not only the familiar black hole interior, but also a mirrored white hole region and another external universe. For a rotating black hole, the internal structure is even more complex, with a ring-shaped singularity, and regions in which paths through space-time can, in principle, pass from one domain to another. Although these exact solutions are not realistic models of astrophysical black holes, they show that the equations naturally allow linked networks of regions in which matter flows inward in some parts and outward in others. This structure makes it easier to imagine how a collapsing region in one space-time could connect through an extreme and brief transition to an expanding region that functions as a new universe. In a white hole interpretation of the Big Bang, the initial state of the universe is not an isolated singularity, but the interface between a black hole collapse and an expanding interior. The properties of the white hole region, such as its total mass content and any net rotation, reflect properties of the original collapsing object. The interior universe then inherits these properties as initial conditions. Its total mass and energy echo the mass that formed the black hole. Its large-scale rotational features, if any, echo the angular momentum of the parent. Over time, as the interior expands and cools, structures such as galaxies and clusters form. Observers in that universe measure the distribution and motions of these structures and infer global properties, yet the deeper origin of those properties lies beyond their observational reach, encoded in the earlier collapse in the parent spacetime. From their point of view, the universe simply begins in a particular state, with a certain density, a certain mixture of matter and radiation, and perhaps subtle large-scale patterns. From the broader point of view of the combined black hole and white hole solution, this beginning is part of a longer chain of events. The usefulness of the white hole concept in this context does not depend on white holes being visible as separate objects in the current universe. Instead, it provides a mathematical language for describing an expanding interior region that is causally disconnected from a parent environment, but dynamically linked to it through shared constants of motion. It allows cosmologists to frame the Big Bang not only as an initial condition applied to the equations, but as a phase in a process that includes both collapse and expansion. In the black hole cosmology hypothesis, the universe that is observed is this interior phase understood as the inside of a white hole that is itself connected to a black hole in a larger space-time. This interpretation presents one possible way in which the same gravitational theory can describe both the origin of a universe and the fate of collapsing matter within a single continuous framework. Rotating black holes form an essential part of the possible connection between a collapsing region in a parent universe and an expanding interior universe. In the simplest case, a non-rotating black hole is described by a solution in which the singularity is a single point and the event horizon is a spherical surface that does not change with time. This description already captures many important features of gravitational collapse, but real astronomical objects almost never lack rotation. Stars, gas clouds, and galaxies all carry angular momentum. When such objects collapse, they spin faster because angular momentum is conserved. It is therefore natural to expect that most black holes in the universe rotate. General relativity describes rotating black holes with a solution discovered in the middle of the 20th century, named after the physicist who first wrote it down. In this solution, the black hole is characterized not only by its mass, but also by its angular momentum. The geometry around it is different from the non-rotating case. Instead of a purely static gravitational field, there is a twisting of space-time itself. This effect is called frame dragging. Nearby matter and even the paths of light are gently pulled around in the direction of the rotation. No object can remain completely at rest with respect to distant stars in the region very close to the rotating black hole. Another feature of a rotating black hole is the appearance of a region outside the event horizon called the ergosphere. Inside the ergosphere, space-time is dragged around so strongly that all possible paths for particles and light have some component in the direction of the black hole's spin. Energy extraction processes are possible in this region in principle, allowing part of the rotational energy of the black hole to be transferred to matter and radiation that escape. Observations of energetic jets and emissions from the surroundings of supermassive black holes suggest that rotation plays an important role in real systems. The internal structure of a rotating black hole, as given by the idealized solution, differs markedly from that of the non-rotating case. The singularity is no longer a point. It takes the form of a ring located in a plane perpendicular to the axis of rotation. The geometry near this ring is complex. In the ideal mathematical solution, there exist paths through space-time that pass through the ring and emerge into other regions that resemble separate universes or different parts of the same extended space-time. These additional regions include both black hole and white hole-like domains, as well as external regions that are not directly connected to the original universe in a simple way. In practice, such extensions are likely to be altered or removed when more realistic conditions and quantum effects are taken into account. However, the presence of a ring-shaped singularity and of multiple internal regions in the rotating solution suggests that rotation may open up possibilities not present in the simpler non-rotating case. For black hole cosmology, the most interesting aspect of a rotating black hole is the way its angular momentum might be communicated to an interior universe. If the collapse of a rotating mass in a parent universe leads after the quantum gravity regime to an expanding interior region, then that region may inherit a preferred axis set by the original spin. The ring singularity in this picture marks the place where the connection between the collapsing and expanding domains is made. The interior universe begins with conditions that include not only a certain total mass and energy, but also a net angular momentum. As the interior expands and cools, matter condenses into structures such as galaxies and clusters. The original spin could then be reflected statistically in the directions of rotation of these structures, or in subtle alignments on the larger scales. The idea that an entire universe could have a small but non-zero overall rotation is not new. Cosmological models have been written in which the large-scale structure of space-time includes a global rotational component. Observations place strong limits on how large such a rotation could be, because significant rotation would leave clear traces in the cosmic microwave background and in the distribution of galaxies. Within those limits, however, a very small rotation is not ruled out. In the black hole universe hypothesis, such a small rotation would be a natural inheritance from a rotating parent black hole. The same frame dragging that forces matter near the horizon of a rotating black hole to share its spin could, in an interior description, be expressed as an overall twisting in the structure of spacetime that gently favors one direction over the opposite. The ring structure of the singularity also supports the idea of an interior expansion. In the non-rotating case, the singularity is a point that all paths within the horizon terminate at. There is no direction in which a path can continue. In the rotating case, the ring leaves a region in its interior where some paths through space-time avoid hitting the singularity. In the ideal solution, these paths can enter new regions. Translating this feature into a realistic model requires understanding how quantum corrections smooth out or replace the singular ring. The general expectation is that quantum gravity would prevent physical quantities from becoming truly infinite, and would instead modify the region near the would-be singularity into a finite but extreme zone where a transition to a new phase can occur. An expanding interior universe can be thought of as one possible outcome of such a transition. The ring singularity of the classical model is then replaced by a small but finite region across which matter and geometry are reconfigured. From the point of view of the interior universe, this region corresponds to the earliest moments of cosmic history, before ordinary matter and radiation settle into the familiar patterns described by standard cosmology. The rotating character of the parent black hole is encoded in the initial conditions of the interior, influencing the small differences between one direction and another that might be detectable in precise surveys of galaxy motions and orientations. Even if such effects are ultimately very subtle, the theory that connects a rotating black hole in a parent universe to an expanding interior universe relies on well-understood aspects of general relativity. It uses the conserved quantities of the collapsing system, such as mass and angular momentum, to set the parameters of the interior. In this way, the existence of rotating black holes becomes more than an astrophysical detail. It becomes a key ingredient in models that seek to understand how a universe like the one that is observed could arise from the interior of a black hole carrying forward the imprint of the rotation of its unseen parent. On the larger scales, cosmology relies on the idea that the universe is statistically simple. When distances are great enough, individual galaxies blur into patterns, and the fine details of shape and orientation give way to averaged properties. This expectation is formalized in the cosmological principle, which states that when viewed on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneity means that any large region of space contains, on average, the same kinds of matter and structures as any other region of similar size. Isotropy means that the universe looks statistically the same in every direction on the sky. No direction is special. This principle underlies the standard cosmological model and has been supported by many observations such as the near uniformity of the cosmic microwave background and the broad similarity of galaxy counts in different parts of the sky. Against this backdrop of expected uniformity, astronomers sometimes look for very small departures that might reveal new physics. One simple property that can be measured for spiral galaxies is the direction in which their arms appear to wind on the sky. Some spirals look from our point of view as though they rotate clockwise. Others look as though they rotate anti-clockwise. The apparent sense of rotation is determined by how the spiral pattern is projected onto the plane of the sky, and it does not tell the full three-dimensional story of the galaxy's motion. but over a large enough sample, the statistics of these orientations should be balanced. If galaxy spins are randomly oriented in space, and if there is no preferred handedness, then the number of clockwise and anti-clockwise spirals seen from Earth should be about the same. This expectation follows from symmetry. There is no obvious reason in a perfectly isotropic universe for nature to favour one apparent direction over the other, when galaxies are counted across a wide region of sky. The James Webb Space Telescope, with its large mirror and sensitive instruments, extends the reach of such studies to much earlier times in cosmic history. It observes faint distant galaxies in detail that was not previously possible from space. In one recent analysis, researchers focus on a set of spiral galaxies located billions of light-years away. From a series of deep images, they identify a sample of a few hundred systems whose spiral structure is clear enough to classify. For each galaxy, they determine whether its arms appear to wind in a pattern that corresponds on the sky to a clockwise rotation or to an anti-clockwise rotation. Counting them yields an unexpected imbalance. Roughly 2/3 of the classified galaxies fall into one apparent direction, while only about 1/3 fall into the other. The exact numbers depend on selection criteria and classification methods, but the trend is that clockwise appearances significantly outnumber anti-clockwise ones in the chosen field. If this result is not due to observational bias or statistical accident, it represents a departure from the simplest form of isotropy. Instead of a random mix, the sky in that region shows a preference. The significance of such an imbalance depends on careful analysis. A relatively small sample can sometimes produce an apparent excess simply by chance, and systematic effects can influence the outcome. For example, the way images are processed, the criteria used to decide whether a spiral is clear enough to classify, and any subtle preferences in how humans or algorithms assign handedness can all introduce asymmetries. The motion of Earth and the orientation of the telescope during observations can also in principle play a role if they correlate with the apparent structure in ways that are not fully accounted for. Because of these possibilities, researchers examine the data from several angles, test different classifications, and consider alternate explanations before proposing any physical interpretation. Even with these cautions, a persistent trend toward one apparent direction in a sample that should be symmetric invites attention. If similar imbalances are seen in other regions of the sky, and if they align along a common axis or show a coherent pattern, they may indicate a small but real large-scale effect. One proposed explanation involves the idea that the universe could possess a tiny global rotation. In such a case, space itself would carry a preferred axis, and the formation of galaxies over cosmic time might reflect this in the aggregate alignment of their spins. The effect on any individual galaxy could be small, overwhelmed by local processes and random variations, but when many galaxies are counted, a slight excess in one-handedness could emerge. In the context of the black hole universe hypothesis, this possibility takes on a different meaning. If the observable universe is the interior of a rotating black hole in a parent spacetime, then the interior geometry inherits the angular momentum of the parent object. The conservation of angular momentum would ensure that the spin of the black hole is encoded in the structure of the interior region. As matter condenses into galaxies inside this region, the preferred axis could influence their typical directions of rotation in a subtle way. An observed imbalance between clockwise and anti-clockwise spirals across the sky would then be one of the signatures that might be expected if such an inherited rotation is present. In that picture, the apparent handedness of spiral galaxies becomes more than a geometric detail. It becomes a probe of the large-scale properties of spacetime itself. The analysis based on James Webb Space Telescope data is one of several attempts over the years to detect such asymmetries. Earlier surveys with ground-based telescopes and other instruments have also reported hints of a preferred handedness in galaxy spins, sometimes along particular directions on the sky. Often, later studies have traced these hints to biases in data selection, classification or coverage, or have found that the significance diminishes when larger samples are considered. The history of these efforts encourages caution. It shows how easy it is for subtle patterns to appear in complex data sets, and how important it is to test whether they persist when methods and samples change. For the moment, the result from the deep James Webb observations sits in this cautious zone. It is an intriguing indication that in at least one set of distant galaxies, there may be a departure from perfect symmetry in spin directions. It is also limited in scope, drawn from a relatively small patch of sky and a finite number of galaxies compared with the vast population that exists. To move beyond suggestion toward firm conclusion, many more galaxies must be examined over much larger areas, using consistent methods that minimize classification bias. Whether future surveys confirm or weaken the reported imbalance, the exercise is valuable. If a real statistically secure asymmetry in galaxy spins is found across the sky, it would challenge the assumption that the universe is isotropic in the simplest sense and would demand an explanation. Global rotation inherited from a parent black hole in a larger spacetime would then be one of several models to consider. If no such asymmetry is found, the cosmological principle emerges strengthened and the observations place tighter limits on any possible rotation of the universe, whether isolated or nested inside a black hole. In both outcomes, careful measurements of how galaxies spin add an empirical layer to discussions that might otherwise remain purely theoretical, linking the fine details of distant spiral arms to questions about the origin and structure of the universe as a whole. In models where the observable universe is treated as the interior of a rotating black hole, the idea of inherited rotation becomes central. A rotating black hole is described in general relativity by its mass and its angular momentum. These two quantities do not disappear when the interior region is considered. Instead, they shape the geometry of spacetime both outside and inside the horizon. Outside frame dragging causes nearby matter and light to be carried around in the direction of spin. Inside, the same angular momentum must be accounted for in any description of how an interior universe develops. Conservation of angular momentum ensures that if the parent object spins, then any region that continues from its interior must in some form share that spin. In this framework, the observable universe is born not from a state with no preferred direction, but from one in which a subtle axis has already been fixed. The early universe, as it expands and cools, is usually described as almost perfectly uniform. Tiny fluctuations in density grow over time to form galaxies and clusters. The standard cosmological model assumes that on the larger scales there is no net rotation. Any local spins are the result of gravitational interactions and random initial conditions. In a black hole cosmology picture, this assumption is relaxed. The overall geometry of the interior spacetime can include a very small global rotation that traces back to the angular momentum of the parent black hole. This rotation need not be large. Observations of the cosmic microwave background and of galaxy distributions place strong limits on any global spin. The temperature pattern of the microwave background is extremely uniform with only small variations. Significant rotation would introduce specific distortions such as alignments or preferred directions that are not seen at a high level. However, a very small rotation could remain hidden within current uncertainties, influencing statistics only in subtle ways. If such a rotation exists, it would act as a background influence on the formation of cosmic structures. As matter in the early universe begins to clump under gravity, small initial fluctuations grow. Gas falls into forming halos, collapses further, and develops rotation through tidal interactions. In a purely non-rotating universe, the directions of these spins would be distributed symmetrically on large scales. In a universe with a tiny inherited rotation, there would be a slight tendency for the spins of many systems to align on average with the original axis. Most individual galaxies would still show a variety of orientations because local processes are complex and often dominant, but when many galaxies are counted, a small excess of one-handedness over the other might emerge. The observed imbalance in apparent spiral rotation directions in some samples has therefore been interpreted in this context as a possible trace of such an inherited axis. If the parent black hole rotates in a particular sense, the interior universe would share that orientation, and the net angular momentum would be distributed among its contents. Over billions of years, as galaxies form and evolve, the original spin could be reflected in the aggregated statistics of their rotations. This picture links a very local measurement, how the arms of a spiral galaxy appear on the sky, to a property of the entire interior space-time. The connection relies on the idea that angular momentum is conserved through the transition from the collapsing parent region to the expanding interior. The mass that collapses to form the black hole carries a certain amount of spin. When quantum gravity effects resolve, there would be singularity and produce an interior universe that spin is not lost. It is built into the geometry of the new region. The details of how this occurs are not yet known because a complete theory of the transition does not yet exist. Nonetheless, the principle of conservation provides a guide. It indicates that whatever the exact mechanism, the total angular momentum of the interior must match that of the collapsing system that formed it. A useful analogy in simpler physics is the collapse of a rotating cloud of gas into a star and surrounding disk. As the cloud contracts, its rotation rate increases, and the resulting star and disk retain the original angular momentum redistributed according to their mass and distance from the center. In the black hole universe scenario, the entire interior space-time plays a role similar to that of the star and disk combined. The original angular momentum of the collapsing matter is spread out through the interior geometry and the structures that later emerge. Unlike the simple example of a gas cloud, however, the black hole case involves extreme gravity and a transition through conditions where classical descriptions fail. The role of rotation does not end with galaxy spins. It can also affect the way large-scale structures arrange themselves. If there is a preferred axis, then the distribution of clusters, voids, and filaments in the cosmic web may show very small statistical preferences aligned with that axis. These would be difficult to detect because the formation of structure is driven by many competing influences, and the random component is strong. Yet in large enough surveys, careful analysis might reveal patterns that are slightly more likely in one orientation than in another. If such patterns match the axis inferred from galaxy spin statistics, they would strengthen the case for a real inherited rotation. In a universe inside a rotating black hole, the light reaching any observer carries information not only about local objects, but also about the global geometry through which it travels. Tiny differences in the travel times and paths of photons caused by an overall twist in space-time might leave imprints in observables, such as polarization patterns in the cosmic microwave background, or correlations between distant structures. Current measurements are not precise enough to rule out all such effects, but they are improving over time. From a theoretical standpoint, constructing detailed models of an interior universe with inherited rotation requires joining a rotating black hole solution in a parent space-time to an expanding cosmological solution in the interior. This involves matching conditions at the boundary that ensure mass angular momentum and other conserved quantities are treated consistently. It also involves incorporating quantum gravity corrections near the region that replaces the classical singularity to avoid unphysical infinities. Several candidate models have been proposed, each making different assumptions about the nature of the transition and the structure of the interior. Despite their differences, they share common features. The interior universe begins with parameters set by the properties of the parent black hole. Its total mass and energy reflect the mass of the collapsed region. Its overall rotation reflects the black hole's angular momentum. Any small charge that the black hole carries might also in principle be reflected, though cosmological observations show that any net charge in the universe must be extremely small. These inherited parameters then guide the later evolution of the interior. In this view, the question of why the universe has its particular large-scale properties is partly answered by pointing to the properties of a parent object. The black hole universe hypothesis thus provides a channel through which the physics of one domain influences another. The rotation observed or tightly constrained in the interior universe becomes an indirect measurement of the rotation of the black hole in the parent spacetime, linking observations made with telescopes to events that by construction can never be seen directly from within the interior itself. Once the possibility is raised that an expanding universe can be understood as the interior of a black hole, another idea follows naturally. If one black hole can contain an interior region that evolves as a universe, then every black hole might have this potential. In that case, the structure of reality would not be a single isolated cosmos, but a branching system of many universes, each linked to others through black holes and their interiors. The universe that is observed would be one member of this larger collection separated from the others by horizons that no signal can cross. In such a framework, each black hole formed in a given universe acts as a seed for a new interior region. When matter collapses to form the black hole, the resulting extreme conditions, together with quantum gravitational effects, produce an expanding domain on the inside. That domain begins in a hot, dense state and cools as it grows, forming its own structures, stars, and galaxies. To observers inside, it appears as a complete universe with its own history, unaware of the parent environment. The horizon that surrounds the original black hole serves as the boundary that isolates the interior. From the outside, nothing beyond that horizon can be seen. From the inside, nothing about the parent universe is accessible. In this way, a single cosmological structure can contain many interior universes, each enclosed by its own horizon and evolving according to the same general physical laws. The concept extends further when the process is repeated. Inside each interior universe, new stars form, live and die. Some of these stars collapse into black holes. If each such black hole again gives rise to its own interior region, then the result is a tree of universes with branches extending through many generations. A universe can be both a child of a parent black hole and a parent to further interior universes created by its own black holes. Over very long timescales, this process could lead to a vast nested arrangement, with a rich variety of interior regions all related through their origin in earlier collapses. In this context, a new kind of selection effect can be imagined. Different universes may have slightly different values for their fundamental parameters, such as the strengths of forces, the masses of particles, or the magnitude of the cosmological constant. These parameters influence how stars form, how long they live, and how often they end their lives as black holes rather than dispersing completely. If each black hole produces a new universe, then universes that are more effective at making black holes will over time generate more descendants. The set of universes that arise in this scenario is then dominated by those whose parameters favor black hole formation. This idea is sometimes described as a form of cosmic natural selection. It does not involve biological evolution, but it follows a similar logic. There is a population of universes. Each universe has parameters that determine, among other things, how many black holes form. Each black hole can give rise to new universes that may inherit parameters similar to those of the parent, perhaps with small variations. Over many generations, universes with parameters that produce more black holes contribute more to the overall population of universes. The result is that typical universes in this ensemble are expected to have properties near those that maximize black hole production under the relevant constraints. In such a framework, the properties of the observable universe might reflect this selection. The strengths of interactions, the balance between radiation, ordinary matter, and dark matter, and the value of the cosmological constant all influence how structure grows. If gravity is too weak or too strong, if matter cools too quickly or too slowly, or if cosmic expansion accelerates too rapidly, the formation of massive stars and black holes can be strongly suppressed. Conversely, there is a broad range of parameter values for which stars and galaxies form efficiently, and for which many stars are massive enough to collapse into black holes at the end of their lives. The universe that is observed falls within such a range. It contains many galaxies, and as far as current observations indicate, enormous numbers of stellar mass and supermassive black holes. From the point of view of standard cosmology, this fact is a result of the measured parameters. From the point of view of cosmic natural selection, it might also be part of the reason those parameters take the values they do. The presence of long-lived stars and complex chemistry which supports the emergence of observers is then a byproduct of conditions that primarily favour black hole production. The idea remains speculative, and many details are unknown. It is not yet clear how parameters would vary between universes, or how closely the parameters of a child universe would track those of its parent. Different models propose different mechanisms for variation. Some suggest that the parameters are fixed by deeper laws and do not vary at all, in which case cosmic natural selection would not operate. Others allow small changes at each transition, which over many generations could produce a variety of parameter combinations. In the absence of direct observational access to other universes, these possibilities are difficult to test. However, the hypothesis does make some indirect suggestions. If the universe is shaped by a process that favours black hole production, then changes to its parameters that would significantly reduce the number of black holes should also lead to universes that are less represented in the ensemble. In principle, it is possible to take the known laws of physics vary certain parameters and calculate how the efficiency of black hole formation would change. If the observed parameters lie near a local maximum of black hole production, in such calculations that would be consistent with the selection picture. If they do not, the picture would be weakened. Work along these lines has been explored at a theoretical level, though the results are not definitive. In any case, the black hole universe hypothesis combined with nested universes and cosmic natural selection offers a broad framework that links the small-scale physics of stellar collapse to the large-scale statistics of universes. It suggests that the familiar cosmos might be one member of a much larger family, and that its basic physical properties could be shaped by the requirement that it produce many black holes capable of seeding further universes. Within this framework, the observable universe retains all the features described by standard cosmology, including an early hot phase expansion and the formation of structure. The additional step is to place this history within a chain of connected regions in which each generation arises inside the black holes of the previous one, carrying forward and perhaps slightly modifying the parameters that govern its evolution. The scales involved in the black hole universe hypothesis are far beyond everyday experience, and even beyond the ranges usually considered in astronomy. A single stellar mass black hole formed from a collapsing star may contain a few times the mass of the Sun within a region only tens of kilometers across. Supermassive black holes in galactic centers can contain millions or billions of solar masses within a volume smaller than the orbit of the outer planets. These objects already represent extremes of density and gravity. The black hole that would be required to contain the entire observable universe, however, lies in a different category altogether. Estimates based on the measured density of matter and energy suggest that the observable universe contains an amount of mass equivalent to roughly 46 trillion suns. Expressed in another way, this is on the order of 10 to the power of 22 times the mass of the Sun. If this mass were concentrated into a single black hole in the manner described by general relativity, the radius of its event horizon would be comparable to the radius of the observable universe, about 14 billion light-years. In this picture, the entire region from which light has had time to reach any given observer since the beginning of cosmic expansion would correspond to the interior of an enormous black hole, and the cosmic horizon seen in all directions would map to its event horizon. To gain a sense of the relative scales, it is useful to compare this hypothetical universe-sized black hole to the supermassive black hole at the centre of the Milky Way. The central object known as Sagittarius, a star, has a mass of a few million suns and a horizon whose diameter is measured in tens of millions of kilometres. Astronomers have imaged the immediate surroundings of similar black holes in other galaxies, using very long baseline radio interferometry, revealing ring-like structures on scales only slightly larger than the orbit of Mercury. If this central black hole is assigned an arbitrary reference size, such as the size of a microscopic particle, then the black hole that would contain the observable universe must be scaled up by an enormous factor to maintain the correct mass ratio. In one such comparison, when Sagittarius A star is reduced to the dimensions of a virus, the corresponding universe-sized black hole would have a diameter similar to that of the Earth. This way of expressing the difference does not capture every detail, but it illustrates how far apart the two objects are in scale, even though both are described by the same underlying theory. The difference in mass between a few million suns and tens of trillions of suns is not just a matter of larger numbers. It changes how the object would fit into a larger environment. A black hole as massive as the one associated with the observable universe would dominate any region of apparent spacetime in which it formed. Its event horizon would span a distance similar to the range over which astronomers currently map galaxies and cosmic structures. From the perspective of an external observer in such a parent universe, this object would be a vast dark sphere, enclosing a volume whose interior is never directly visible. From the perspective of internal observers, the same structure would be experienced as an expanding universe with a finite horizon. No measurement made from within could reveal the full external size of the enclosing black hole. Another aspect of scale is the enormous range of densities involved during different phases of the interior universe. At very early times, the energy density is extremely high, with matter and radiation tightly coupled. As expansion proceeds, the density drop structures form and the universe becomes transparent to light. Throughout this history, the total mass and energy remain fixed in the black hole universe, picture set by the amount of matter that originally collapsed in the parent spacetime. The way that mass and energy are arranged changes dramatically, but the sum does not. This contrasts with the way the same process appears in the parent environment. There, the formation of the black hole looks like a concentration of matter into a smaller and smaller region, with density increasing over time until the horizon forms and the interior becomes causally disconnected. The interior and exterior descriptions use different language, but they apply to the same physical configuration of space-time. The scales considered also highlight how neatly general relativity connects mass, distance, and time through a small set of constants. The gravitational radius associated with the mass of the observable universe naturally turns out to be of the same order as the distance light has travelled since the beginning of expansion. This convergence is not imposed by hand. It arises because the same constants that govern black holes also govern cosmology. In units adapted to these constants, the separation between what seems small and what seems large becomes less arbitrary. A black hole with a mass of tens of trillions of suns and a universe with a horizon tens of billions of light-years across share a common description. Both are particular ways that space-time can organize mass and energy. For human intuition built on experiences with planets, stars, and perhaps the central regions of galaxies, The leap from ordinary astronomical scales to the scales involved in a universe-sized black hole is daunting. Yet in the equations, the transition is smooth. The same mathematical framework that predicts the horizon of a small black hole also yields the horizon of a cosmic one. This continuity is part of what makes the black hole universe hypothesis conceptually attractive. It does not require a new kind of object to contain an interior universe. It requires only an extension of familiar gravitational behavior to a domain where mass and size reach values far beyond those encountered in direct observation, but still follow the same rules. From a broader perspective, these scales emphasize how a single set of physical laws can generate structures that range from microscopic particles to entire universes. The black hole universe hypothesis uses this single set of laws to link the largest possible object, a universe-sized black hole, to the detailed contents of the interior cosmos that is measured with telescopes. In the standard picture of cosmic history, the early universe passes through a very brief phase of extremely rapid expansion known as inflation. This idea is introduced to address several puzzles that arise if the universe simply expands at a steady pace from the beginning. One puzzle is the horizon problem. Observations of the cosmic microwave background show that regions of the sky separated by large angles have almost exactly the same temperature, even though without inflation there would not have been enough time for light or any other signal to travel between them and establish such uniformity. Inflation resolves this by proposing that before the visible expansion phase, the universe was much smaller and more closely connected. A short but intense period of accelerated expansion then stretched this region to a size far larger than the observable universe today. Regions that now appear widely separated were once close enough to share information and reach thermal equilibrium. Another puzzle is the flatness problem. Measurements indicate that the geometry of the universe is very close to spatially flat, meaning that on large scales space is not strongly curved either positively or negatively. Without inflation, it would be difficult to understand why the universe began in such a finely balanced state. Small deviations from flatness tend to grow over time. Inflation, by contrast, naturally drives the geometry toward flatness by stretching any initial curvature over a much larger scale. The result is a universe that appears nearly flat when observed billions of years later. Inflation also plays a role in generating the small imperfections that seed the growth of structure. Quantum fluctuations in the field that drives inflation are stretched to macroscopic scales and become tiny variations in density. After inflation ends, these variations serve as the starting points for the formation of galaxies and clusters. Regions that are slightly denser than average attract more matter and grow over time, while regions that are slightly less dense become voids. The pattern of these early fluctuations is imprinted in the cosmic microwave background as small temperature variations around an almost uniform value. Precision measurements of this pattern show a spectrum of fluctuations that aligns well with the expectations of simple, inflationary models. As the universe evolves, the initially smooth distribution of matter becomes more structured. Galaxies merge and gather into clusters. Filaments and walls of galaxies outline a cosmic web with large empty spaces between them. Despite this richness, the overall arrangement remains statistically simple on the largest scales. When very large volumes are considered, the distribution of matter becomes homogeneous, and the directions of structures appear isotropic within the limits of current observations. The combination of inflation and standard cosmic expansion thus produces a universe that is nearly smooth with small, well-understood imperfections that grow into the structures seen today. In the black hole universe hypothesis, the early history of the interior region must account for these same observations. Any interior universe that is to resemble the one that is measured must reproduce to high accuracy the near uniformity of the cosmic microwave background, the specific pattern of its fluctuations, and the large-scale homogeneity and isotropy of matter. One way to do this is to include an inflationary phase in the interior, much like the one used in standard cosmology. In this case, the interior universe experiences rapid expansion after the transition that replaces the classical singularity. The inflationary field smooths out irregularities inherited from the collapse in the parent spacetime and generates its own spectrum of fluctuations. By the time ordinary cosmic expansion begins, the interior universe looks much like a standard inflating universe that has emerged from a hot, dense state. The details of the connection between the collapsing parent and the inflating interior are not fully known because they depend on the physics of extreme densities and quantum gravity. However, the requirement that the interior reproduce the observed cosmic microwave background and large-scale structure places strong constraints on any model. It suggests that if the universe is inside a black hole, the transition must allow for an inflationary phase or some mechanism with similar smoothing and fluctuation generating effects. Even with such smoothing, small imperfections remain and are expected. These imperfections are not flaws in the model. They are essential features that lead to structure. The temperature variations in the microwave background are at the level of 1 part in 100,000, and the resulting density contrasts eventually grow into galaxies and clusters. The distribution of these imperfections is highly regular in its statistical properties, and it is this regularity that allows inflationary models to be tested. Observations have revealed a few features that do not fit perfectly into the simplest expectations, such as slight alignments of large-scale modes in the microwave background, or small tensions between the inferred expansion rate from different data sets. These features are often called anomalies. Their significance is a matter of ongoing study, and they may eventually be traced to statistical chance unrecognized systematics, or more complex but still standard physics. In the context of a black hole interior, such anomalies become possible places to look for residual traces of the parent collapse. For example, if the parent black hole had a small amount of rotation, or other large-scale structure that was not completely smoothed out by inflation, it might leave very faint signatures in the interior universe. These could appear as tiny deviations from perfect isotropy, as subtle preferences in the alignment of structures, or as patterns in the distribution of galaxies that differ slightly from the simplest random expectations. The reported imbalance in spiral galaxy rotation directions in some surveys is one example of a potential imperfection that might be interpreted in this way, although its status remains uncertain. Other possible hints include correlations over large angles in the microwave background or alignments in the orientations of galaxy clusters. For each of these, standard cosmology offers potential explanations, and in many cases the evidence is not strong enough to claim a new effect. The black hole universe picture does not replace these explanations. Instead, it offers an alternative viewpoint in which some of the same anomalies could be understood as inherited features from a parent spacetime. The key question is whether any consistent pattern emerges that cannot be accounted for by the usual combination of inflation and cosmic expansion alone. If future observations find that the universe is even more uniform than current data suggest, with anomalies shrinking as measurements improve, then the freedom for any inherited structures from a parent black hole becomes small. In that case, if the universe is inside a black hole, the transition and any interior inflation must be extremely effective at erasing prior information. If, however, certain patterns persist and grow more pronounced as data accumulate, and if they match the kind of residuals expected from a rotating or otherwise structured parent collapse, then the black hole universe hypothesis gains a more specific observational role. It becomes not just a conceptual possibility, but a framework in which concrete deviations from the simplest cosmological models can be interpreted. In both situations, the small imperfections in the cosmic pattern act as a sensitive test. They sit at the boundary between a universe that can be described entirely as an isolated system with its own initial conditions and a universe whose initial conditions are themselves the outcome of processes in a larger unseen environment. Within the scientific community, ideas that link the entire universe to the interior of a black hole are treated with cautious interest rather than broad acceptance. Standard cosmology built on the cosmological principle, general relativity, and a simple inventory of matter and energy has been very successful in explaining a wide range of observations. It accounts for the expansion of the universe, the pattern of the cosmic microwave background, the formation of large-scale structure, and the abundances of light elements created in the early hot phase. Any alternative or extended picture such as black hole cosmology is expected to reproduce these successes at least as well before it can be considered a serious rival. For this reason, many researchers regard the black hole universe hypothesis not as a replacement for the standard model, but as a speculative interpretation that must be examined carefully against the same data. Skepticism is particularly strong when new claims appear to challenge the cosmological principle. Observations that suggest a preferred direction on the sky, or an imbalance in some property that should be symmetric, attract attention, but also invite detailed scrutiny. The reported asymmetry in spiral galaxy rotation directions is an example. Counting a few hundred galaxies in a deep field and finding that about 2/3 appear to rotate one way, and 1/3 the other is interesting, but it is not yet definitive. A relatively small sample can produce an apparent imbalance through statistical fluctuation alone. Moreover, the process of classifying galaxies is subtle. Image quality noise and the orientation of spiral arms can affect how a system is labeled. Human classifiers may introduce unconscious biases, and automated algorithms can be sensitive to details of image processing and training. Previous studies have encountered similar challenges. Analyses of older surveys have at times reported hints of a preferred handedness in galaxy spins or alignments of structures along particular axes. Later work has often shown that these patterns weaken or disappear when larger samples are used, when data from different telescopes are combined, or when improved methods correct for biases. This history encourages a conservative attitude toward any new claim of large-scale asymmetry. Many cosmologists prefer to treat such results as provisional until they are confirmed independently by multiple data sets and methods. In the case of the James Webb observations, the field of view is small compared with the entire sky, and the number of galaxies examined is a tiny fraction of the full population. Until similar analyses are carried out over many other regions using consistent techniques and careful control of systematics, it remains uncertain whether the imbalance represents a real feature of the universe or a local fluctuation. Beyond specific observations, there are broader conceptual concerns. Some physicists question whether the internal region of a black hole can genuinely be identified with a full-fledged universe rather than with a transient configuration that quickly ends at a singularity. Others point out that the idealized solutions of general relativity that link black holes and white holes are highly symmetric and may not apply to the messy conditions of real gravitational collapse. In realistic scenarios, rotation, magnetic fields, turbulence, and quantum effects all play a role. These factors can disrupt the delicate structures seen in exact solutions, and may prevent the formation of the extended networks of regions that are often drawn in diagrams of maximally extended black holes. Without a detailed, physically motivated model of how a collapsing star or cloud in a parent spacetime produces an interior universe, with the observed properties, many researchers prefer to regard the black hole universe idea as a useful thought experiment rather than a concrete description. There is also the question of testability. A strong scientific theory not only accommodates existing data, but also makes clear predictions that can at least in principle be checked. If the observable universe is inside a black hole, the exterior region and the larger environment in which that black hole resides are by construction inaccessible to observation. The horizon that separates the interior from the parent universe blocks any direct signal. This makes it difficult to design tests that distinguish an interior universe from an isolated one. Proponents of the black hole universe hypothesis point to potential indirect signatures such as small global rotations, subtle departures from perfect isotropy, or patterns in the distribution of galaxies that could reflect inherited properties from the parent black hole. Critics reply that many of these signatures can also be produced or explained away within the standard cosmological framework by adjusting initial conditions, refining models of inflation, or incorporating known astrophysical processes. Another concern arises from the current absence of a complete theory of quantum gravity. The most critical part of the black hole universe scenario lies in the regime where classical general relativity fails near the would-be singularity. It is there that the transition from a collapsing region in the parent universe to an expanding interior universe is supposed to occur. Without a well-established quantum gravity theory, descriptions of this transition remain schematic. Different approaches suggest different outcomes, and it is not yet known whether the conditions required for a stable interior universe are generic or rare. Some approaches imply that singularities are replaced by bounces that connect phases within a single universe rather than by bridges to new universes. Others suggest that information is preserved in ways that make simple, interior universe pictures hard to maintain. Until these deep issues are resolved, black hole cosmology rests on assumptions about extreme physics that are not yet grounded in a unified framework. Despite these reservations, the hypothesis continues to attract attention from a subset of researchers because it ties together several otherwise separate puzzles. It offers an intuitive way to connect the singularities of cosmology and black hole physics, and it provides a possible context for numerical coincidences such as the match between the mass and size of the observable universe and those of a corresponding black hole horizon. It also offers a setting in which ideas about nested universes and cosmic natural selection can be explored quantitatively. For others, these same features highlight the speculative character of the proposal. They argue that the appeal of such a unifying picture must be weighed against the current lack of decisive evidence and the success of more conservative models. In practice, the black hole universe hypothesis occupies an intermediate position. It is not ruled out by existing data, but it is not required to explain them. It remains a framework in which certain questions about the origin and structure of the universe can be posed in a new way, waiting for future observations and theoretical advances to clarify whether this way of posing them reflects the actual architecture of space-time or simply one of many mathematically consistent possibilities that nature does not use. At the heart of the black hole universe hypothesis lies a question about what can in principle be known. Cosmology already works with horizons that limit observation. The particle horizon defines how far light has travelled since the beginning of expansion. The cosmic event horizon in models with accelerated expansion defines which regions can ever send signals that arrive in the future. These boundaries are not technical details. They are features of space-time that set permanent limits on access to information. The idea that the observable universe might be the interior of a black hole adds another layer to this picture. In such a scenario, the event horizon of a black hole in a parent spacetime coincides from the point of view of internal observers with the cosmic boundary. No signal can cross from the interior to the exterior or from the exterior to the interior. If this is the case, then the question of whether the universe is inside a black hole may not have an operational answer. Observers inside would never be able to send probes beyond the horizon or receive messages from the parent environment. All measurements, no matter how advanced, would be confined to the interior region. They would reveal the contents and geometry of that region in increasing detail, but they would not show directly how or whether it connects to a larger structure. In practice, cosmology is already conducted under similar constraints. The observable universe is treated as a self-contained system because nothing outside the horizon can be measured. Initial conditions are inferred from current observations and known physical laws. The Big Bang is represented as an early state from which the later universe evolves. Whether that early state is an absolute beginning or a transition from a previous phase is not decided by direct observation. It is decided, if at all, by theoretical arguments and indirect evidence. The black hole universe hypothesis fits naturally into this pattern. It proposes that the initial state of the observable universe is the result of gravitational collapse in apparent space-time. It uses the structures of general relativity to support the idea that an interior universe can exist beyond what would otherwise be a singularity, and that this interior can evolve as an expanding cosmos. It points to parallels between horizon singularities and mass scales as suggestive. It looks to small deviations from perfect isotropy, such as possible excesses of one galaxy's spin-handedness, as places where inherited features from a parent black hole might appear. At the same time, it acknowledges that all of this rests on extrapolations into a regime where classical gravity fails, and quantum gravity has not yet been fully formulated. From the standpoint of scientific method, this leaves the hypothesis in a delicate position. It is constrained by observations because any interior universe must match the measured properties of the cosmos. It is guided by established theory because it uses known solutions of general relativity as its foundation. Yet it reaches beyond both into domains where neither direct measurement nor fully tested theory operate. This is not unique. Many proposals about the earliest moments of the universe, the global structure of space-time or the behavior of singularities share this feature. They are attempts to extend understanding into regions where data are scarce, and the equations themselves signal incompleteness. The black hole universe hypothesis stands among these as one more attempt to give a coherent account of how the universe might emerge from known physics. The limits imposed by horizons make it likely that no simple observation will ever distinguish definitively between an isolated universe that begins in an initial state and an interior universe that continues from apparent collapse. Instead, progress, if it comes, will depend on a convergence of clues. Improved measurements of the cosmic microwave background galaxy distributions and gravitational waves may reveal whether any large-scale rotations or alignments exist beyond the level expected from chance and standard processes. Advances in theoretical work on quantum gravity may clarify whether transitions from collapsing regions to expanding interiors are generic or rare, and what signatures they would leave. Studies of how physical parameters affect black hole formation may show whether the observed universe sits near a point that maximizes such formation, lending support to ideas of cosmic natural selection. Even if these efforts eventually favor or disfavor the black hole universe picture, the underlying question remains the same. It concerns whether the observable universe should be treated as a complete whole or as one region in a larger layered structure of space-time. In both views, observers are bounded by horizons. In both views, the earliest moments of cosmic history occur under conditions where current theories are incomplete. The difference lies in how these unknowns are organized. One view places the universe at the top level with its initial state given. The other places it as an interior region with that initial state derived from processes in a parent environment. For now, the data do not compel a choice. The observable universe behaves as though it follows the rules of general relativity and standard cosmology, with inflation expansion and structure formation proceeding in a way that matches measurements to high precision. The speculative addition that this entire interior may reside within a black hole in another spacetime is consistent with many of these features, but not demanded by them. It remains an open possibility anchored by mathematics, and enriched by new observations yet bounded by the same horizons that limit all cosmological inquiry, the question of whether the universe is inside a black hole is therefore not only a question about external structure, it is also a question about how far physical explanation can extend in a cosmos where some regions are by definition forever beyond reach.